Are we okay to start? Not sure, just waiting.
Can't actually hear anything in the VC. Give me 30 seconds.
Okay. 1 minute, everybody. Can you hear me now okay? We're just checking on our recording equipment, everyone. Apologies for the slight delay. All right.
But the recording's good and in here's good.
Yes, they can hear. I can see it. Thank you for replying. Welcome everyone to the Next in the Research Skills seminar series. My name's Sue Scull and I run the Research Education Program here at CARS. If you've never attended one of these seminars before, the idea is we generally cover a very large topic in just an hour, so we're very much about designing information for very busy clinical people, trying to fit research around the margins, and throughout the year we cover over 20 topics, all of which you'll find on our website as well. We really take pride in our handouts and make sure there's extra information in there for you in terms of extra websites and if we know about them, training opportunities. And please fill in the evaluation form link. It's very, very quick and we do take on board your feedback and try and improve what we do each year. So thank you for doing that. Do we have a second microphone on at the moment? No. Okay. Okay. People out there, put your microphones on mute. And because we do record all around and video link around Western Australia, please hold your questions to the end, but even if you're offline, we can see your questions and we'll help you there. And just a small announcement that we are back on track now after having had to put up a couple of 2019 versions of seminars. We always have a complete set of our seminars online that you can read along with our handouts. But if you want the most up-to-date information, come to the seminars in person and ask questions. But we're back on track as normal now for the rest of the year. So I'd now like to introduce Julie Marsh, who's a very experienced statistical consultant, and Julie's worked across academia, private industry, and is now a senior research fellow with particular expertise in adaptive trials methodology at Telethon Kids Institute. And not only is she talking to us today, but she's presenting a really fantastic new seminar next week as well. So please join me in thanking Julie and welcome her to the lectern.
Good afternoon, isn't it now? I'd like to acknowledge the land that we stand on and with the traditional owners and pay my respects to elders past, present and future. I'm very honoured to work in partnership with them on many of my research projects, and I really appreciate their wisdom and their humour. Okay. So for all of you who have struggled through stats courses, today I'm not going to emphasise formulae, algebra. There will be a little bit of scary subscripting and superscripts on these, but you can just close your eyes when it all gets a bit too much. I'm trying to get over concepts today. There's lots of web information, but if you don't understand the language we're talking to begin with, it can be quite difficult to even get involved. So I'm afraid there's lots of slides today, so I'm going to whiz through them. They are designed for someone who maybe is unable to attend and just wants to read the slides. So I'm just going to pick out the salient points on each of them. Okay. So just your learning outcomes, just in case you're wondering if you're the right seminar today. So just to make sure everyone's familiar with the difference between observational and experimental studies, what the differences is between chance, bias, and confounding. The statisticians go on and on about variability, interpreting the results from statistical hypothesis tests, and understanding the importance of objective reporting of experimental studies. So important, so much published, and we still have issues around the peer review process. So if you take nothing else away from this today, please stop just reading the abstract. If something is worth you getting to the end of the abstract, please just flick through the methods and make sure, is this appropriate? Is this how I would have done it? You know, what's the credibility in this methodology? Okay. So for anyone who's unfamiliar, I'll just race through. An observational study is where we don't intervene. It's very much, we just observe as natural processes or procedures or policies or protocols are followed within our health system. Experimental studies is where we intervene. Hopefully we've previously observed what's happened. We control as many elements as we can, and we change one small part of it. And particularly if you get right down to at the bottom there, when we talk about randomized control trials, we really can start looking at causal effects, as opposed to association, where two things appear to be related, but we don't know the causality implications in those studies. I predominantly work on experimental studies over this side, so you have to excuse all my examples coming from that side. Oops. So just to confuse the rest of the world, I have to say it's very nice at the moment. People actually want to talk to statisticians at the moment because we tend to understand numbers. So rather than being just ignored in the lift, I find people talking to me about R0 nowadays.
All participants are now muted.
Okay, so let me just explain some of the code that we do talk in. So we've already spoken previously what an observational study is, but let's just pick apart some of the other words we use for that. So the first word is inference. And what we really mean there as a biased statistician is we're guessing, really, the properties of the population. But it doesn't feel very technical to say that we're guessing, so we tend to say that we infer something or we use inference. And the types of things we guess, for example, of if I took all the heights of the people in the room here, and for those at home, there's 20 people very nicely spaced in here, all having washed their hands before they come in, I hope. So,
just ask everyone to turn off their microphones. We're having constant problems.
I'm afraid there's a lot of feedback here, and it's not just laughing at my humour. If anybody still has their microphone, could you please mute them, just to stop the feedback in the lecture theatre here? Thank you. So when we talk about inference, we're really saying we're guessing the underlying distribution. For example, if we looked at the heights of everybody in the room here, we would guess that they're approximately normally distributed. And by having an underlying statistical distribution, we're able to generalize our results. We're able to build variability around it. So when we use inference, we're basically guessing under, and that's where the word parametric comes from. Most of the distributions are parametric. They're based on a normal distribution or a gamma or lots of other nasty Greek letters that we use. The other important part is we can't measure everyone. We can't do unlimited number of experiments. We're often limited by our resources, such as costs or people's times, or sometimes if it's a rare disease, the number of individuals who are living with that particular condition. So we take samples. So a sample is just a set of data collected, and ideally it's selected in a framework, which means it's representative of the overall target population that we're trying to draw conclusions about. And the statistical population is also called the target population. It's really when you use eligibility, so inclusion, exclusion. You know, who are we saying this is generalizable to? If you only recruit males into your population, you can't really infer anything about the female's response to a similar intervention. When we talk about the independent variable, it's the variable that is changed or controlled in experimental design. However, when you're looking at observational designs, it's usually whether they're exposed or not exposed. And the last one is when we talk about control, I think it's very important nowadays that we don't use excuses not to include a control or at least a comparator group. And it refers to the technique of separating out the effect of one independent variable on the outcome. Yeah, so quite often for the control we use standard of care, or we may use, for our new drug, we may be interested in placebo if there's nothing available on the market, but increasingly we're looking at comparative effectiveness. Let's just move on. I spoke earlier about with experimental designs, we have the option of looking at causality when we drill down to a design such as a randomized controlled trial. Whereas in the observational data sets, when we come up with the magic p-values, or people say there's an association or a relationship, we are really looking at saying that when A happens, we tend to see B, rather than saying that A causes B. So there's that very large difference between association and causation. And don't worry, if you accidentally write the wrong word in your publication, you will be picked up by numerous reviewers. Okay, let's just move on. So the three things that we really focus in with experimental design are association, where it's being controlled, and also the variability. Okay. So in a good design, we try to minimize the variability, and that's within the treatment, the exposure, or the intervention groups. What we're trying to do is push down the costs of our research. We can't study as many people as we want, or as many mice, or as many samples in the laboratory. We're trying to operate under minimal costs. So in which case we have to control the variability. I'm going to come back to this later when we talk about sample size and determine how big our experiment needs to be. In health research, the highest level of evidence is always a randomized controlled trial. So I'll just take you through this design very briefly. So this is the simplest possible design, where there are two arms that we're studying. We have group 1 and group 2. In this case, group 1 receives the new treatment and group 2 is the control treatment. It may be placebo, it may be standard of care, it may be a sham placebo if we're looking at different surgeries. Okay. The dice here represents a process called randomization. What we don't want is systematic bias. So maybe all the males receive the new treatment, all the females the control treatment. Or there are all other subtle biases. So for example, if all patients who turn up on a Monday go on to the new treatment and all patients on Tuesday go on to the control, it may be certain bus routes operate on different days, so people turn up. It may be, if you're recruiting elderly patients, pension day is payout on a Wednesday when they go shopping, so they're more likely to turn up at other days of the week. There are all subtle biases that can come into the experiment. So we randomize them. As each patient walks in consecutively, we use the equivalent of throwing a dice or tossing a coin to allocate them to the different treatment arms. However, it doesn't look very professional if you're rolling the dice in front of them in the surgery and that, so we tend to do it all using computer algorithms with validated seed number generators. Validated random number generators. And the reason we do the randomization is we're trying to control all those other confounding factors. We want to know that at baseline, those in group 1 have roughly similar characteristics to those in group 2. However, a common fallacy is that they have to be absolutely identical and that you need to test all the baseline variables in those two groups. you can include these variables as in the statistical model in your analysis. Okay? So it's not the end of the world if you don't get complete balance, but in general, we should have approximate balance across the groups at baseline. And the last bit of jargon is generalizability. So it goes back to the previous examples. If we've only studied males, we can only draw conclusions about males. If we've only studied the elderly, we can only draw conclusions about those. So we talk about the results of a randomized control trial having internal validity. Yeah, we randomize, the groups have similar characteristics, so within the study we know that they are comparable. We have that internal validity between them. However, what we're interested in doing is looking at the external validity of our study. And these characteristics are determined by the inclusion-exclusion criteria. So hopefully, the group that we study in, for example, our controlled trial will be similar to the patients who are walking in day to day into the hospital or into general practice. Apologies for not being able to stop for questions, but I'm sure, as you can imagine, it's quite difficult to do it over all different locations. So please save them up for the end, or hang around for a little while later. And I believe Sue said they can come in as written. Can they enter them on the comments? But they're different things as well? Okay, cool. So I'm going to move on to chance, confounding, and bias, because they all seem to be mixed up in one big lump. Let's split all those out. So chance is really what we're interested in. Okay. What's the chances this could have, what is the likelihood that these results could have happened by chance? Okay. Or is there a relationship? If we think the odds of this occurring by chance are so rare, we start inferring that the intervention is what's causing the effect. However, there are a couple of things we have to minimize first. And one of those is bias. Now, bias is a really big bad word. There is nothing we can do once we get bias into our study. We can't adjust for it like we can with confounders. So these are often systematic errors it could be in the design or the recruitment, the data collection, or even in the analysis that's used. So all we can do with bias is try and design it out in the very beginning. A good start with bias is learn from others what they've done in a similar situation. And that means drilling down to those previous publications and look at their strengths and weaknesses. Look at all the things that previous investigators wish they had have done before they started their experiment. On the next couple of slides, I've written common sources of bias, and they will apply to some of your studies and not to others. So I'll just leave that as a little background reading for anyone, but please do try and tick them off as you design your studies. The good problem we have is confounding factors. And again, we're trying to minimize the differences between our two groups that we're comparing. Okay? So we want them to have equal numbers with these confounding factors in each of the groups. So a confounder is where the relationship between the intervention or the exposure and the outcome is distorted by another variable. So in this example, we look at an outcome of cardiovascular disease. We have cardiovascular disease over here. And this particular study looked at the effect of coffee drinking. But the problem we have is smoking. High levels of current smokers tend to drink more coffee than those who don't smoke. And we know that smoking itself is also associated with cardiovascular disease. In this case, smoking is a confounder. It is associated with both the factor, which is coffee drinking, and with the outcome, which is cardiovascular disease. For those who like a bit of algebra, that's put in a more statistical framework, but the rest of us just close our eyes. It's really good to look at the effects of confounding in systematic reviews. And this one took that same coffee drinking and broke it down into, they looked at it overall. What if you ignored all the confounders and just looked at the relationship? So this is implying that higher levels of coffee drinking is more protective against cardiovascular disease. It feels a little counterintuitive. You would have thought that it would have lie across this line here with neither protective nor harmful. However, when you start breaking it down into the different confounders, you find it going off into different directions, which would imply in this study just looking at everybody overall and just adding them to all together, or what we call aggregating over all the different confounders, can quite often either arbitrarily create a pattern or, in some cases, it can bias it towards the null effect where you see no pattern. So it's always good to break things out by your different confounders. It just gives you a fuller picture. Language itself in the papers that you're reading can also distort the evidence, and it's important to be objective. You often hear people say there is strong evidence, just because the p-value is very, very small. So strength is subjective. It's very important that people present a point estimate, a confidence interval, and a p-value. And then you get to use your own judgment of whether you think that's strong evidence or otherwise. Yeah? So be cautious about the language which is used in publications. It's far more important to focus on the size of effect. You may have a p-value which is very close to 0, but an effect size which has no clinical relevance whatsoever. We have ways of addressing chance bias and confounding and trying to minimize any problems from these. So I would strongly recommend, particularly if you're doing clinical trials, that you look through good clinical practice and experimental design guidelines. And really what we're trying to do there is remove bias and minimize confounding. With the hypothesis test, it allows us to evaluate what is the probability, or what is the chance, what is the likelihood that we would have observed these results by chance alone. Our confidence intervals allow us to see how precise is this estimate. Is it highly variable? So they may present a point estimate of, there's an increase, 8-fold increase, but if your confidence interval goes from close to 0 up to 100, there could be no difference, there could be 100-fold difference. It's so wide to make the results fairly meaningless. So always look at the confidence interval. How precise is this point? Because they often present a single point number. We want to know how variable that is. And the reporting guidelines, which I'll refer to at the end, have certainly taken us many steps forward in terms of standardizing how we report things. So I'm going to move on to sampling error first, because as I mentioned earlier, we don't have the resources to sample everybody, to test every sample. So when we talk about a representative sample, we have the whole population that we're interested in over here. We don't have the resources to test or measure all the time and to do all these individuals. So we want to take what we call a random sample out. And quite often in consultation with a statistician, you'll come up with a framework and a way of sampling from these individuals to ensure that if the average age in your target population, say, is age 55, then you would hope by sampling you would get a similar average age in your sample population. And you may look at factors such as social demographics, it may be the region they come from, it could be the age, it could be gender. But we're trying to get our mini sample here. We want a mini-me here, of what we observe in the characteristics in this population over here. But we only take one sample. We only have the resources to take that sample once. So it's really important to get that right. However, the whole basis for hypothesis testing itself is the idea of what if we took multiple samples? What if we took the same sample again, again, and again? Sorry, there are some interesting noises online. Again, if anybody is listening, please can you ensure that you've muted your microphone? So hypothesis testing is used to quantify our belief that our current results, remember this is belief in just the sample of data that we've collected. Yeah? So we want to quantify our belief that our current results are due to chance alone. But first we need to model the data using a probability distribution, and part of that is understanding the underlying variability in the results. We call this the sampling error. And the best way to think of this is, say we were interested in measuring the birth weights for a group of children. We could measure them here at King Eddie's, or we could go to another, we could go to the home birthing unit and record all the birth weights from babies born there, or we could pick up from antenatal classes and sample from individuals there. We could also do it in Western Australia, we could do it in Tasmania, we could do it in Northern Territories. There are all different samples you could take in all different ways. Sampling error addresses the idea of what if that's exactly what we did? This is our current sample, but hypothetically, what if we took the sample again? And what if we took the sample again in Brisbane? What if we took the sample again in Sydney? What if we sampled again sorry, I've gone blank today, in Darwin? If we took the mean birth weight from each one of those hypothetical samples, we could build another distribution. So it's the idea that birth weight itself, for example, is approximately normally distributed for full-term babies. So we have that underlying variability in birth weight, but also if we collected mean birth weight again and again and again from multiple hypothetical samples, the mean itself, the mean birth rate itself, has its own sampling distribution. Yeah? So there's the variability in birth weight, and there's the variability in mean birth weight itself. So it's the variability in the mean. So when we come up with a mean of, say, 2.4 kilograms, we come up with a mean of 2.4 kilograms in Perth, but we come up with a mean of 2.35 kilograms in Darwin, we come up with a mean of 2.5 kilograms in Melbourne. You see, the mean itself is varying from sample to sample across those different locations. So the mean itself has an underlying distribution, and we call that the sampling distribution. You also hear that called the standard error, or the variation in that mean is the standard error. Oops. So just to remind you, that's a histogram, for example, if this was birth weights, full-term birth weights. And the normal distribution has two shape parameters. It's centered around its mean. So this has a mean here of about -2. This one has a mean of 0. There's a slight lag in this mouse, sorry. There's a mean here of 0 and the red curve, and there's a mean here in the yellow curve. So we talk about the normal distribution having two shape parameters. That's its mean and its standard deviation. So as your mean changes, so for example, between the green to the blue, you get that shift left and right on the axis. As the variation changes, so keeping the mean fixed here, so the yellow, the red, and the blue, they're all normal distributions. They all have exactly the same mean of 0, but this time they have different values for their standard deviation. So this yellow here has a large standard deviation of 5, This one has a smaller standard deviation of 1, right? Red is 1, and then blue has the smallest standard deviation of 0.5. So you can see that shape of that distribution, the flattening or peakiness, is determined by the variation, and then that translation or shifting along the axis is determined by the mean value. The reason we are obsessed with the shape of the normal distribution, and this is a probability density function here, is because we know that the area under here tells us the probability of observing something. So the area under the curve, under these normal distributions, gives us a probability. But what we can't do as statisticians, so I was educated in the era where we didn't really use computers much and we used to hand calculate everything. It was only my final year at university they actually let us loose on software, and we didn't have to do even linear regression by hand anymore. Gives you an idea of how old I am. I was lucky not to do punch cards though, so that kind of puts me in that era. So the last thing we could do was walk around with big statistical tables for every possible mean and standard deviation of a normal distribution and look up what the probability was for that area under the curve. And so there's a really nice trick with the normal distribution where no matter what its mean and standard deviation is, yeah, if you take a value, you subtract the mean and divide by the standard error, everything goes back to a standard normal. And a standard normal has a mean of 0 and a standard deviation of 1. So all it is a little trick we do. So we only use one set of statistical tables rather than have to carry a different set of statistical tables for every possible shape you can imagine for the normal distribution. And that's the reason when you perform, I think I've got it on the next slide. Sorry. Sorry, it comes up later on, but that's the reason why we're always subtracting a mean and dividing by a variance whenever we do anything which is based on the normal distribution. We're just reverting everything back to that standardized normal curve so we can read the area under the curve and tell you what the probability is. So getting back to the sampling distribution, remember we're taking all that samples from all those different cities of birth weight. And this is the sampling distribution about the mean birth weight. So it's not the underlying distribution of birth weight itself, it's the distribution for the mean. Yeah? And we denote that by X bar. And we say it's normally distributed, it's centered around the true population value, and it has a standard error given over here by the variance divided by the sample size. So you can see the bigger your sample size, the smaller your standard error, and the tighter or more precise your estimate's going to get, because you get these more peaky distributions. So the bigger n is, the smaller your standard error is, the less variation in your sample mean, the more precise your estimate's going to be from your experiment. So that's the reason statisticians always say, how big an n can you give me? However, in many experiments, particularly with mice experiments or the very early stage, first in man and those types of experiments, we're looking at very small sample sizes, in which case we use the student's t-distribution. Now it's very similar to the normal distribution, and you can see the two different shapes here. So in black is the normal distribution, and in red is the t-distribution. And again, we're obsessed with the area under the curve because it gives us probabilities. That's why shape matters. Okay. What the t-distribution gives you when you have small numbers is you're slightly more likely to get tail values. So we have what we call chunkier tails. So rather than just a nice smooth normal distribution, yeah, it tends to be a little bit flatter and a bit chunkier tails. Yeah, we're more likely to see extreme events when we get down into small sample sizes. The reason we don't see those extreme events so much with the larger sample sizes is they all get lost in large numbers. If one person is 2 meters tall out of 100, they're going to have less effect on the sample as opposed to one person out of 10 who is 2 meters tall. So just to give you an idea, the t-distribution is similar to the normal, similar in shape, thicker tails. So for a typical study with n equals 6 could be a mouse study. When you get a typical phase 1 study, about 12 individuals, you'll see they're getting closer and closer together. And by the time you get to sample sizes in excess of 120, there is no difference between using a t-distribution and a normal distribution. So just a little aside there, why we use the t-distribution. So just to finish off on sampling error, the accuracy of the sample mean depends on its sampling error, and the sampling error comes from the sample standard deviation and the sample size itself. The bigger your sample size, the more precise your sample mean will be. And just to say that often we don't know what this population variation is, and so we estimate it with the sample standard deviation instead. And that's why in many of your formulae you'll see that value S divided by root n. Okay, for that. So now I'm going to move on to confidence intervals. And I'm going to use that simple birth rate example all the way through this. And again, when you see the algebra, if it gets too scary, don't worry about it. It's the general principles we're trying to get here, rather than teach formulae. Okay.
All participants are now muted.
So say we had a sample of 152 babies. So that immediately gives us our sample size. I've calculated the mean for you, and it's 3.3 kilograms. I've calculated the standard deviation. And once we have the sample mean and the standard deviation, we can calculate the standard error.
All participants are now
muted. And remember, the standard error is telling us how variable is our mean. Yeah? So that's simply the sample standard deviation divided by root n. Okay. And confidence intervals are simply an easy to interpret way of expressing the precision with which a statistic, in this case the sample mean, estimates a parameter. We want to know what the population value of birth weight is. Okay, for any of those who are interested, the next few lines of algebra show you where the confidence interval comes from. Okay. So in here, we standardize to get a standardized normal, and we do that by subtracting the mean, the population mean, and dividing by the variability. Yeah? So our sample mean here could have had any mean value and any variation, but by subtracting the population value and dividing by its variance, we change it into a standard normal, which has a mean of 0 and a standard deviation of 1.
Oh, Sophie's gone to Annabelle.
And once we know that, we know the area under the curve here from the properties of the normal distribution. Yeah? So if we go minus 1.96 units of the standard deviation away from the mean, and then plus 1.96 units of standard deviation above the mean, we know the area under the curve there is 0.95 or 95%. So that tells us that Z, if it lies between minus 1.96 and 1.96 for a standard normal, because remember the standard deviation is 1, so if it lies between those two, we know that the probability of that is 0.95. But we have the formula for Z up here. Yeah, so we can simply replace Z with its formula in here. We can rearrange it around the population birth weight parameter there. And that gives you your classic 95% confidence interval. Yeah? The sample mean plus or minus 1.96 times the standard error. So for this particular example, it gives us a 95% confidence interval of 3.25 to 3.39. Yeah, just plug in the numbers in. But how do we interpret this? So a confidence interval gives a range of plausible values for a parameter in light of the observed data. Yeah? So this confidence interval only holds for this particular sample. If we had a different sample in Darwin, we'd have a different 95% confidence interval, because they would have had a different sample mean and a different standard error. If we look at the sample from Melbourne and the sample from Hobart, we'd get all different values. So the confidence interval really comes with the idea of sample, resample, sample again, and it's all these hypothetical samples. So the classical way a statistician is taught is we say if a very large number of random samples, all of the same size, were collected from a population, and a 95% confidence interval computed for each one of those samples, so Melbourne, Hobart, Perth, etc., then the true value of the parameter, so that's mu, the population value, would lie in about 95% of these intervals. So graphically, it might be easier to understand that. So these were just all randomly calculated confidence intervals, and they were all based on the value 100. Okay? So you would imagine that often people assume, well, the population value has to lie in there because you've randomly sampled from that, so every confidence interval should contain it. But as you can see here, there are 20 confidence intervals, and just by chance, about 1 in 20 times, you can get a confidence interval that doesn't contain the true value given by this line here. Yeah? So by chance alone, we may have sampled lots and lots of lower birth weight or lower height or lower value. Okay. And you end up with a confidence interval that doesn't contain the true value. So just because you produce a confidence interval, it doesn't mean the true value lies smack bang in the middle of your confidence interval for your current data. It just means if you repeated the sample again and again, 95% of all those samples would contain this true value 100. So stop focusing on the midpoint of your confidence interval, yeah? Think of the whole range as a plausible range for the true estimate to lie in. And this use of our 95%, yeah? Yeah? So if it lies in 95% of those samples, it means it doesn't lie in 5% of them. And that's what we call our type 1 error. So when we talk about a significance level or type 1 error, when we refer to that as 5% or 0.05 or 1 in 20. They all mean exactly the same. That's what our type 1 error is. So just recapping, the standard error gives us the level of precision of our estimate. We can calculate a confidence interval, and the confidence interval gives us the range of plausible values for the true population parameter. But it doesn't necessarily mean the best estimate lies right smack bang in the middle of that confidence interval. But what we have to decide is still, what is the probability I would have obtained this set of data due to chance alone under the null hypothesis? So moving from confidence intervals to hypothesis testing, and by the way, hypothesis testing is also called significance testing. I won't go into, there is a subtle difference between the two of them, but nowadays we all do hypothesis tests where we take into account the type 1 and the type 2 error. Okay. But what has changed here from the confidence interval, where we haven't assumed any null distribution, to calculate a p-value or probability of observing this by chance, yeah, we assume a null hypothesis. Okay. So a hypothesis test is a hypothesis that is testable on the basis on the basis of observing a process that is modelled via a set of random variables. Now you get all these pretty hard definitions written in statistical textbooks where you read them and you think, absolutely, I'm no clearer whatsoever. So let's just walk through an example of that. So say we want to know, we've looked up from previous years and tables that the mean birth weight is 3.4 kilograms. Yeah? So we want to know from our current sample if that value's changed or not. So under the null hypothesis, we say that the true mean birth weight is still 3.4 kilograms. And we make our alternate hypothesis that it's not equal to it. And this is where you get that expression, a two-tailed test. So when we say it's not equal to, it can be greater than or less than. So we have to look in both tails of the distribution when we calculate what's the probability of it being greater, what's the probability of it being less. Is it that one? Okay. So some of you may be familiar with the formula. So we take the sample mean, we minus the population parameter from our null hypothesis, and we divide by the standard error. So we can put all of those values, we can all put all of those values in there from what we calculated earlier. The sample mean, that was from our null hypothesis, 3.4 kilograms, and we divide by the standard error we calculated earlier. And we get what we call a z-score. So z-score is likely to take values close to 0 if the null hypothesis is correct, i.e. the true value really is 3.4 kilograms, or it's likely to take extreme positive or negative values if the null hypothesis is incorrect. So what we want to know, is minus 2.33 sufficiently extreme to cause us to reject the null hypothesis? And we have a convention around this. So when we calculate the p-value, we say it's defined to be the probability of getting a test statistic, such as your z-score in this case, at least as extreme as the one observed. But it's always under the assumption that h0 is true. So all hypothesis tests are performed under the null hypothesis. So how likely are we to see 2.33 or minus 2.33? Remember, it's a two-tailed test. We have to look at both ends of that distribution. Yeah. So we're using a standardized normal because we subtracted the mean and divided by the standard error. We're using a standardized normal. We got a z-score of minus 2.33. It's a two-tailed test, so we add up the area under the curve for plus 2.3. And it's the probability of observing that test statistic or something more extreme. Hence, we look at the two tails, we add those two probabilities together, and that's how we get our p-value. Yeah, so p-values are also, what's the probability of observing this test statistic or something more extreme under the null hypothesis? Or basically, what's the likelihood I would have observed this by chance? And we use the value 0.05. Remember, it goes back to that type 1 error again. We're willing to take the risk of occasionally falsely rejecting the null hypothesis. So we look at our p-value, 0.0198. We compare that to the value 0.05. It's clearly less than, so we reject the null hypothesis. We only reject or fail to reject a null hypothesis. We never accept. Okay, we reject or we fail to reject. But the question, so remember the three things we talked about earlier: a point estimate, a confidence interval, and a p-value. So we have all three of those now. But it's not for me to tell you whether that's strong evidence or anything else, and it's only for you to interpret whether you would consider this confidence interval as a nice precise estimate or not, and your own interpretation of results. Yeah? So don't let the papers push you in any particular direction. It's important for you to draw your own conclusions on it. This is saying that there is a difference between the two, but whether it is clinically relevant is another question. Now, statistical analysis, unfortunately I can't teach you very many statistical analysis in the next 10 minutes. I'm still learning all the different methodologies there are. You can only be a specialist in a very small area. It's such a wide field nowadays. But I am putting up a resource here. So for any of you looking for which is the right statistical test to do, this is a great site which is supported by the University of California in Los Angeles. and they provide all manner of different tests. For example, a one-sample t-test, a two-sample test of medians and all the rest of it. They let you say how many dependent variables you have. Okay, and they give you example code in whatever is your preferred statistical package as well. So I can't teach you statistical tests today. In fact, just teaching that linear regression is a whole unit at UWA, and that's just the most basic linear regression, never mind the more specialist areas. But I would recommend this particular website, which are in the slides. Okay. And obviously I'd recommend talking to a statistician or seeing what access you have to free statistical support that way as well. The advantage of having a statistician as one of your supervisors if you're a student is, of course, you get unlimited free statistical support all the time and someone who's going to check all your figures and tables. Okay. So we've talked previously about your type 1 error. That's the probability of rejecting something that's rejected the null hypothesis when it's true, and that's equivalent of it falling in these red tails. So what if, under the red curve here, the null hypothesis is true, but by chance you can still get values that fall in these tails. Yeah? And that's where we get our 5% when they fall in these tails. The power of a test, so the blue curve here represents the alternate hypothesis. Yeah? But again, by chance, you can get something under the alternate hypothesis that by chance your sample mean or your z-score may end up in this region over here. Now it belongs under the blue curve, but it's hit that cutoff. Yeah? It's hit that cutoff, in which case we falsely fail to reject the null hypothesis. And we call that the type 2 error. That little blue area there, we call the type 2 error. So it truly belongs to the alternate hypothesis, but because it's this side of the line, we fail to reject the null hypothesis. That coloured in blue area there represents our type 2 error, and 1 minus our type 2 error tells us the power of a study. In this one, it's completely overpowered because it's at 96.7%. Normally power is between 80 to 90%. So that's covered your type 1, your type 2 errors, and the last bit that's missing is your sample size. And remember, your sample size comes into your standard error, and your standard error determines your precision of your effect. Okay, so we control the sample size, we control the type 1 error and the type 2 error, and that determines whether it's a valid study or not, whether it's sufficiently large or whether you're unable to draw any conclusions from it. Okay. So when we look at standardized reporting, we give the p-value. Could we have observed this by chance? We give the estimate of effect size. Is it clinically relevant? We provide the confidence interval, saying what is the precision of what's been presented to us. Okay, and we infer the causality, but we cannot infer causality unless it's a design such a randomized control trial. There are guidelines for causality. I believe many people still quote the Bradford Hill criteria. It will depend on your research area. So the last thing I'm going to cover today is standardized reporting. We do have reporting guidelines published for many different types of study. So for example, the consort, I believe the consort is randomized control trials. Forgive me if I get these wrong. Trend is for non-randomized studies, and I believe observational studies as well. Intervention studies. Strobe is for observational studies, can't remember which the other ones were. I believe that's for Prisma is for pragmatic or meta-analysis, isn't it? I can't remember they're all for, and there's others for GWAS studies, if you're looking at the genetic studies, but there's a whole range of reporting guidelines, and even within each of these guidelines, they are expanded. For example, the consort stage statement has been expanded into adaptive trials, it's been and into, say, step wedge designs and that. So do please, before you do any research, pick up these reporting guidelines. They give you a really handy checklist that says, have you thought of? And many publications themselves some of the reviewers will pick up your manuscript and these checklists, and they will make sure they can tick off all the elements on that checklist before they submit you for peer review even further. So with these guidelines, do consult them before you even design the study, as well as you're planning the design, as you're planning the analysis, and definitely when you're writing the paper. And if you don't read them until after you've submitted the paper, you might get some very long reviewer comments that come back that you have to respond to. So by using standardized reporting, it takes away some of that guesswork of what did these authors do. Can I trust these results is really what you're looking at. And by adhering to these reporting guidelines and the checklists that they have, it allows us to present results in a standardized way, so we can also compare studies that have been done in different countries or maybe with slightly different interventions, and we can make comparisons between things, because you want to build up a body of knowledge. If you see one study reported, I wouldn't completely believe it until you found another group that can replicate it. And even if another group's replicated it, you can't ensure that the other 20 groups that tried to replicate it couldn't get it published, because we also get that publication bias that comes in as well. Okay, so just to emphasize, we went through all the different jargon around observational and experimental studies. We looked at the effect of chance bias and confounding. We looked at the importance of variability, interpreting the results of our p-value, and the fundamental importance of objective reporting of health data in the journals. That's everything for today. I'll hand back over to Sue.
Thank you, Julie. That was very comprehensive in just 1 hour, or just under an hour. Does anyone have any questions or comments for Julie? And I'll also duck over there and see if there are any in the audience as well. Please go ahead. Don't be shy.
Do you want me to give a quick plug for next week then?
Yes, do that.
And if anybody has any studies which have been impacted by COVID-19, which I would imagine it should be just about everyone. I can't imagine there are a few research protocols which haven't been affected by it. Next week the seminar is all based on what actions do you need to take, what plan do you need in place, how does the analysis change, how does the protocol change, what discussions should you have in, for example, your trial steering group. So I'm going to cover the consensus we've had from the Australian network of statisticians about that next week.
I can't see any comments online. So please take a moment. You'll be emailed the link if you can't access it or type it in yourself, just to do a very quick evaluation for us, which will help us and Julie for next time. And please join me in thanking Julie for a great coverage of a very large topic today. And thank you for persevering with the people joining us. It's always tricky.